example 5.1. Determine the output voltage V out using node and using simple circuits. So I'm going to use two methods to calculate the output voltage of this op amp. So by me doing that, what I'm going to do here is I'll start off with node and then do simple circuits. So here we go. So this is the node method. So let's punch in the circuit, and then we should define our nodes. So to do our counting, what I'm going to do here is that the obvious one is our ground right here. Then I'm going to say that this is V1, just because when it's attached to the negative, we are automatically call that V1. And then I'm going to have this blue node right here, which is what we call V2. So one obvious note here is that you could see here is that this guy has to be 3 volts because it's that connected to the ground. And then our output voltage is this green node right here. And this is V out. So if I do the counting, note that there are, so let's do the counting. So I see that I have two unknown nodes. So I have 3 nodes, but I have one source. So the nodes that I'm really looking for are nodes 1 and 2. So I have 2 node equations. So I have node 1, node 2, but note that I can't write a node equation for V out, so I have to use the ideal model to give me that second equation. So then I have 3 equations, 3 unknowns, which will be V1, V2, V out. So let's go apply it now. So if I go and I apply it, I'm going to come up here and I'm going to say, okay, here's my first equation. This is going to be node equation 1. So if I look at 1, you can see that there are 2 resistors, 1 mutual, no current sources. So I'm going to have 10, 20 times V1 minus 20 V out equals to 0. So then if I look at node 2 tells me that there's nothing connected to node 1, so I'm going to get 0. Then I have node 2, and I can see that I have 2 resistors at 10 and a 20. And then this is V2. And then I have that 10K connected to the 3 volts. So then I'm going to go minus 10 times 3, and that's equal to 0. So if you look at this thing, look at that. I have V2, V1, V out. That's 3 unknowns, but 2 equations. But now I have the ideal model. And what does the ideal model tells me? Well, I know that this current is equal to 0, and I know that this current is equal to 0, but that doesn't really tell me anything. So the condition of I1 equal to I2 equal to 0, this tells us nothing. But the second condition, which is V1 has to be equal to V2, you could immediately see that if I set these two guys equal to each other, that really tells me that I have an equation that reads V1 minus V2 equals to 0. Okay? So then now I'm gonna matrix this thing up and write a solution here. So this is my third equation, is V1 minus V2. So then I'm gonna matrix up and get solution. So if I just do the standard thing that we typically do here, I have V1, V2, V out. So if I look at V1, I have one here, and I have not there, but right here. So I have two entries. So I have 10 plus 20. I have 0, and then my second one is 1. So now let's go look for V2. So V2 is right here, and it's right there. So then I'm going to get 0, and then I'm going to have 10 and 20, and then I'm going to have minus 1. And then finally, I have V out here. That's the only place I have it. Right? I don't have V out any other place here. So then when I write this, it's going to read minus 1 over 20. Then I'm going to get 0, 0. So here's my matrix. And then I have my constants. And if I look at my constants, you could see here that this guy's going to give me 0, and this is going to give me 3/10. But when I take it to the other side, so I'm really talking about that guy right there, and I'm talking about 0 right there. So if I add that, I'm going to get 0, 3/10, 0. Then my solution for V out gives me plus 6 volts. So there it is. I'm not a huge fan for this for op amps. My preferred method is to use simple circuit methods. And what I do here is that what's very important here is that I apply immediately the conditions of the op amp right away. So I'm going to come up here, since I've already highlighted this, I'm going to copy this, and I'm going to bring it down here. So what I have a tendency to do when I do simple circuits here is that I follow the current. And feel what goes on. So that means I immediately apply I1, I2 equal to 0, and V1, V2 are the same. So let's go do that. So what I'm going to do here is that if I paste my circuit, here it is. So what do I know? Okay. So if I look at my circuit, I'm going to get rid of these currents here for right now, just so that we can walk through. So I'm going to use the exact same nodes that we talked about before. So the first thing that I'm going to see here is that if I look at the condition, okay, so now let's look at conditions. So this is the condition of the ideal model of I1, I2 equals to 0. So what does that mean? Well, what that means here is that this guy is I1 equal to 0. So now I got to follow the current. So if I look at the current, V1 has a current that's going to go through the 10K. In other words, I expect a current to go this way. So the current goes from V1 down to ground. And if I follow this up, note that if no current goes through this I1 equal to 0 branch, then that same current is the same right there. So that means here, what I'm really saying is that what this tells me here is that the current of the left 10K has to be equal to the top 10K. So they must have the same current. Now let's look at the next condition. V1 equals to V2. So what you're seeing here is that, note, this tells me right here that this I2 is 0. So what this is saying here is that there's going to be a current flow that flows in this direction. No current goes into the op amp. So that tells me here, this condition then tells us here that the 3-volt source, that 10K, and the 20K are in series. So if they're in series, I'm going to use VDR to calculate V2, which is the same as the 20K resistor. So V2, which is the same as the 20K resistor, well, that has to be 10 plus 20 divided into 20 times 3 volts. I get a value of plus 2 volts for V2. But what this tells me here is that the ideal model immediately says that, wait a minute, V1 and V2 are the same, and they have the exact same value of V2. All of a sudden, I know what the voltage is, what voltage V1 is. So now I'm going to focus on the 10K resistor between V1 and ground. So remember, I know that the 10K and the 20K have the same current. So if I calculate the 10K current, that's got to be V1 minus 0 divided by 10K, which is, of course, 2 minus 0 divided by 10K, which then gives me 0.2 milliamps. But that's the current of the 10K, but it's also the current of the 20K. So I now know what that current is, right? I now know what that current is. So now that I have that current, what I'm going to do now is I'm going to apply Ohm's law. Okay, so that means I'm going to apply Ohm's law to top 20 kilo ohm resistor. So look what happens here. So if I look at this, I have my resistor, and here's my 20K, right? Here's my 20K, and I know for a fact that this current of the 20K is going in this direction, and that current is 0.2 milliamps. So this node right here, this is V1, which is 2 volts. And then I have this other node, which is V out. So now if I apply Ohm's law, you could then see here that this should be V out minus V1 should be the current of the 20K times this 0.2 milli. And so if I multiply everything out here, you're going to see here is that I'm going to get what? That's 20 times 0.2. That should give me 4. So then this tells me here is that V out should be V1 plus 4 volts, which then gives me positive 6 volts for V out.